extraterrestrial life enters a new chapter with a stunning discovery from the James Webb Space Telescope. While observing exoplanet K2-18b, scientists found its atmosphere filled with strong chemical signatures of life. Specifically, the gases dimethyl sulfide, abbreviated as DMS, and dimethyl disulfide, abbreviated as DMDS, which are only produced on Earth by living organisms, primarily by marine microorganisms like phytoplankton or algae. According to scientists, this breakthrough discovery not only suggests a world possibly teeming with microorganisms but also raises hope that humans are closer than ever to answering the question, are we alone in the universe? Professor Niku Madhusudan, an astrophysicist at Cambridge University who leads the research team, said, "This is the strongest evidence to date of potential biological activity outside our solar system. We are very cautious. We must question both whether the signal is real and, if so, what it truly means." He also added that decades from now, we may look back at this moment and realize that the living universe was truly within our grasp. This could be a turning point where the fundamental question, are we alone in the universe, has an answer. Located 124 light-years from Earth, planet K2-18b is in the constellation Leo, with a mass nearly 9 times that of Earth and a diameter 2.6 times larger. It orbits a red dwarf star that is cooler and smaller than the Sun, and notably lies within the habitable zone around a star, meaning the region where water can exist in liquid form. The habitable zone or Goldilocks zone is an extremely important concept in the search for extraterrestrial life. As the name implies, this is the area of space around a star where the surface temperature of a planet could allow liquid water to exist. And as we know, liquid water is considered a key ingredient for life as we know it. When the Hubble telescope detected a possible water vapor signal in K2-18b's atmosphere in 2019, scientists once proclaimed this as the most habitable world known outside our solar system. However, in subsequent observations in 2023 by the team of Madhusudan himself, the signal thought to be water was re-identified as methane. Nevertheless, the research team still argues that K2-18b's characteristics are consistent with a potentially habitable planet, possibly covered by a deep and vast ocean. However, this claim remains controversial. Exoplanets like K2-18b are too far away to be directly imaged or reached by spacecraft. However, scientists can estimate their size, material density, and temperature, as well as analyze the chemical composition of the planet's atmosphere when they pass in front of their host star, by measuring the starlight filtered through the planet's atmosphere. Scientists observed that wavelengths absorbed by DMS and DMDS sharply decreased when K2-18b transited the red dwarf star, meaning K2-18b's atmosphere shows signs of these two substances. Professor Madhusudan said, "The signal appears clear and strong if we can detect these molecules on potentially habitable planets. Then this is the first time humanity has done so. It's incredible to know this is feasible." Published in the Astrophysical Journal Letters. The new findings suggest that the concentration of DMS, DMDS, or both, since their signals are mixed, could be thousands of times higher than levels found on Earth. This result achieves a statistical confidence level of 3 sigma, meaning the probability of it occurring randomly is 0.3%. The research team believes there may be unknown processes producing these molecules. but we don't think there is currently any abiotic mechanism that can explain this. However, some scientists remain skeptical, arguing that there are still many doubts about both K2 to 18b's ability to support life and whether DMS or DMDS, typically produced by marine organisms on Earth, are truly reliable biosignatures, given the unknown atmospheric conditions of K2 to 18b. Could still produce DMS and DMDS by some means. While Professor Madhusudan's team leans toward the hypothesis that this planet has an ocean, other scientists argue that data from the James Webb Telescope fits a gas planet or one covered by magma. They also raise further questions about whether stellar flares brought DMS to K2-18b. Additionally, there is a hypothesis that DMS could be generated in hydrothermal vents. Volcanoes or lightning storms through unusual chemical reactions. Dr. Norhan, a chemist at the Penn Institute of Physics, said, "Life's existence is one possibility, but only one among many hypotheses. We need to completely rule out all other possibilities before we can claim the existence of life." Other chemists argue that measuring the planet's atmosphere alone is insufficient to provide clear evidence of life. What the chemical community has not properly assessed is technosyndactyl, like a signal intercepted from an advanced civilization, could be much clearer evidence even though the probability of detecting them is extremely low. This discovery is still an important step forward, but chemists still need to maintain caution regarding any claims related to life. Not because extraterrestrial life does not exist, but because a revolutionary discovery like this requires an extremely solid level of evidence. With a distance of 120 light-years, verification through direct observation is impossible, at least in the near future. However, Professor Madhusudan notes that this was never an obstacle when humans discovered black holes or other cosmic phenomena. He emphasized, "We are trying to determine whether biological laws are universal in the universe. I don't think we need to swim in water to catch fish." Assuming that if the mechanism producing TMS and DMTS is proven similar on any planet, star system, or corner of the universe, then the signal from K18b is a sign of life, regardless of whether we can verify it there or not. Extraterrestrial life may not resemble anything we have ever seen on Earth. Trying to find evidence of these unknown organisms will require some creativity. We only have one example of biological formation in the universe, which is life on Earth. But what if life can form in other ways? How can we search for extraterrestrial life when we don't know what extraterrestrial life looks like? These questions are puzzling astrobiologists, scientists who search for extraterrestrial life. Astrobiologists have attempted to establish general rules governing the emergence of complex physical and biological systems on and beyond Earth. According to astronomy professor Jared Impey, from the University of Arizona, the most common form of extraterrestrial life could be microorganisms, since single cells can form more easily than larger organisms. Since the first discovery of an exoplanet in 1995, over 5,000 exoplanets or planets orbiting other stars have been found. Many of these exoplanets are small and rocky, similar to Earth, and also located in habitable zones. The habitable zone is the range of distance between a planet's surface and the star it orbits, allowing the planet to have liquid water and subsequently support life as we know it on Earth. The sample of exoplanets discovered so far predicts 300 million potential biological experiments in our galaxy, or 300 million locations including exoplanets and other celestial bodies like moons, with suitable biological conditions. The uncertainty for researchers begins with the definition of life. It seems that defining life is easy because we know life exists when observing a bird flying or a bacterium moving in a drop of water. But scientists do not agree on a definition, and some argue that a comprehensive definition is impossible. NASA defines life as a self-sustaining chemical reaction capable of Darwinian evolution. That means organisms with complex chemical systems evolve by adapting to their environment. S theory of evolution states that an organism Exoplanets are distant and hundreds of millions of times dimmer than their host stars, so studying them is a challenge. Astronomers can examine the atmospheres and surfaces of Earth like exoplanets using a method called spectroscopy to search for chemical signs of life. Spectroscopy can detect signs of oxygen in a planet's atmosphere that cyanobacteria produced through photosynthesis on Earth billions of years ago, or signs of chlorophyll indicating plant life. S definition of life leads to some important but unanswered questions. Is Darwin What chemical reactions could produce extraterrestrial organisms? All life on Earth, from fungal spores to blue whales, evolved from a common bacterial ancestor 4 billion years ago. Similar chemical processes are found in all living organisms on Earth, and those processes might be universal. But they could also be completely different elsewhere. In October 2024, a group of scientists gathered to bring fresh thinking to the theory of evolution. They wanted to step back and explore which processes created order in the universe, whether biological or not, to find studies of life emergence completely different from life on Earth. Two researchers presented arguments that complex chemical and mineral systems, when in environments allowing some configurations to exist better than others, will evolve to store larger amounts of information. Over time, the system becomes more diverse and complex, achieving functions necessary for survival through natural selection. They speculated that there might be a law describing the evolution of various physical systems. Biological evolution, through natural selection, is just one example of this broader law. In biology, information relates to instructions stored in the sequence of nucleotides on DNA molecules, together forming an organism's genome and determining what the organism looks like and how it functions. If we interpret complexity through information theory, natural selection will make the genome more complex as it stores more information about its environment. Complexity can be useful in measuring the boundary between life and non-life. However, concluding that animals are more complex than bacteria is inaccurate. Biological information increases the genome size, but evolutionary information density decreases. Evolutionary information density is the ratio of functional genes in the genome, where the proportion of total genetic material is less than adequate. Organisms we consider primitive, such as bacteria, possess genomes with high information density and thus appear better designed than the genomes of plants or animals. The universal theory of life remains elusive. Such a theory would include concepts of complexity and information storage, but it would not be tied to DNA or specific cell types we find in organisms on Earth. All living organisms from bacteria to humans contain water, and it is the essential solvent for life on Earth. A solvent is a liquid medium that facilitates chemical reactions from which life can emerge. However, life could also arise from other solvents. Astrobiologists William Penn and Sajah Shinger have discovered thousands of molecules related to life. Suitable solvents include sulfuric acid, amurix, liquid carbon rheosine, and even liquid sulfur. Extraterrestrial life may not rely on carbon, which forms the backbone of all essential life molecules, at least on Earth. It might not even need a planet to exist. Advanced life forms on other planets could be so strange that we wouldn't recognize them. As astrobiologists try to detect extraterrestrial life, they will need to be creative. One strategy is to measure mineral signatures on the rocky surfaces of exoplanets because mineral diversity tracks evolutionary processes. As life evolved on Earth, it used and created minerals for exoskeletons and habitats. The hundreds of minerals present when life first formed have increased to about 5,000 today. Another strategy to find non-Earth-like life is to detect evidence of a civilization, such as artificial light or nitrogen dioxide in the atmosphere. These are examples of technosignatures of intelligent life. It is still unclear how and when the first extraterrestrial life will be discovered. It could be within the solar system by examining the atmospheres of exoplanets, or by detecting artificial radio signals from a distant civilization. If the faint signal from K28b is the first whisper of life, then another recent discovery opens a completely different door. A door leading into the hearts of giant planets. This time, the SEMR-18 telescope not only listens to light from distant worlds but also looks directly into their atmospheres. For the first time in history, scientists have directly imaged Cancitiosite, the characteristic chemical signature from a planet outside the solar system. This is not only a technological leap but also a strategic advance in understanding how planets and possibly life form among the stars. And that remarkable story begins with a very young planetary system, only 30 million years old. Previously, detecting the presence of onheosites in exoplanet atmospheres relied mainly on indirect methods. Analyzing the light spectrum from stars when a planet passes in front. However, thanks to SEMR-18's infrared observation capability and advanced light blocking technology, scientists can for the first time directly see a trace of this gas in the atmosphere of a distant planet. The planet observed by SEMR-18 belongs to the HR 8799 system, a special planetary system only 30 million years old. Much younger than the 4.6 million-year-old solar system. This system has long attracted researchers' interest in planet formation due to its many giant gas planets with characteristics similar to Jupiter and Saturn. The new discovery from SEMR-18 provides strong evidence that planets in HR 8799 form through a core accretion mechanism. A process where a giant planet starts by accumulating solid material before attracting surrounding gas. This is also the formation mechanism of gas planets in the solar system, supporting the theory that planet formation in the universe may follow common principles. William Pomer, an astrophysicist at Johns Hopkins University and the study's lead, emphasized that detecting strong carbon dioxide signatures in these planets' atmospheres is a crucial step. He stated that by detecting these strong carbon dioxide signatures, we have demonstrated that there is a significant amount of heavy elements like carbon, oxygen, and iron in these planets' atmospheres, based on what we know about the star they orbit. This supports the theory that they formed by core accretion. A very important conclusion for exoplanets we can directly observe. Directly observing exoplanets is no small challenge, because their light is very faint compared to the dazzling light from their host stars. However, James Webb has major advantages like infrared observation capability. allowing it to detect thermal light emitted by young planets still cooling after formation. In particular, planet HR8799e in the HR8799 system is emitting large amounts of heat for its formation process, making it glow strongly in the infrared region. Thanks to this, James Webb can accurately record important atmospheric signals from this planet. One of the key tools helping James Webb achieve this success is the coronagraph, a device capable of blocking light from the host star to reveal the fainter light of orbiting planets. This technology works similarly to an artificial eclipse, helping scientists see worlds hidden behind the host star's blinding light. Thanks to coronagraph, James Webb can collect infrared data in the 3 to 5 micron range, providing detailed information on the chemical composition of exoplanet atmosphere. This observation not only confirms the presence of ions, but also helps scientists better understand the atmospheric composition of our 8799e. They discovered that this planet contains more heavy elements than previously predicted, supporting the hypothesis that it formed in a similar way to gas planets in the solar system. This is an important discovery, as it helps identify key factors in the planet formation process, as well as the role of chemical compounds or heavy elements in the evolution of planetary atmospheres. Previously, scientists could only speculate about the chemical composition of exoplanets using indirect methods, such as observing changes in the light spectrum when a planet passes in front of its host star. But with SEM-LUST, they can directly analyze the infrared light emitted by the planet, allowing for more accurate study of its atmosphere and environmental conditions. Another important discovery is that SEM-LUST has captured the first direct image of planet HR8799e at a wavelength of 4.6 microns and Eridani B at a wavelength of 4.1 microns. These observations highlight the telescope's extraordinary sensitivity in capturing faint planetary signals, even when they are located close to a bright host star. This opens up opportunities to study more exoplanets in habitable zones, where atmospheric conditions might allow life to exist. Analyzing the chemical composition of exoplanet atmospheres not only helps determine how they form, but also explores the possibility of life in the universe. If a planet has carbon dioxide but also water vapor, methane, or oxygen, it might suggest Earth-like climate conditions, increasing the likelihood of finding signs of extraterrestrial life. These discoveries are significant not only for planetary science but also for understanding the formation and evolution of planetary systems. William Pomer emphasized that these giant planets have special significance. If such a planet drifted into the solar system, it could cause serious disruption, protect, or even destroy smaller planets like Earth. Therefore, studying their formation will help us better understand how rocky planets like Earth can exist and evolve in the universe. Understanding the formation and evolution of giant gas planets not only sheds light on the history of the solar system but also helps identify the necessary factors to sustain life on other planets. This discovery has been published in the Astrophysical Journal and marks a major advancement in modern astronomical research. This has been developed for giant planets, and giant planets can exist and evolve in planetary systems. This has been developed for giant planets, and giant planets can exist and evolve in planetary systems. Thank you for watching the video.